Hello and welcome to Richardson's RFPD's Tech Chat. My name is Simon Tomkins. I'm Senior Field Application Engineer at Richardson RFPD. I'm here today talking with Guy Moxey, who's Senior Marketing Director at Wolfspeed, and we will be discussing SiC MOSFET RDS-on over temperature. Guy, thank you so much for joining us today.
Hey Simon, pleasure to be here. Thanks.
In this chat, we will look at the conduction losses of SiC MOSFETs from Wolfspeed. Guy, can you help us to understand how the RDS-on of Wolfspeed's SiC FETs compare to other available technologies, please?
Yeah, thank you for bringing this up, Simon, because a lot of people migrate to silicon carbide due to its switching performance, which is clear. But there is one other huge difference that we at Wolfspeed have really focused on, which is RDS-on over temperature, that conduction loss as well. And you can see from this chart, and this is not every single one of our technologies, but it's a general design principle. This is a 650 volt part, for example, how our conduction loss is relatively flat over temperature. Now, unfortunately, it's not completely flat. That would be a utopian switch, wouldn't it? But, you know, at 25 degrees C, datasheet value, you know, it's, in this case, it's going to be 60 milliohms, for example. But as the temperature increases to where you would actually use this part, a junction temperature of 125 up to 175 degrees C, you'll see that our conduction loss, our RDS-on, only really increases by around about typically 1.3x over temperature. Whereas if you chose a GaN part, for example, or a superjunction CoolMOS type of part in silicon, you can see both of those technologies will increase 2 to 2.5 times over temperature. So what this does mean that, you know, when you're using a device where you need it, when it's hot, you don't have to pick a datasheet to datasheet direct comparison because you will be overrating silicon carbide. You know, a 60 milliohm device is 90 milliohms hot. Whereas, you know, a silicon device, you would have to be choosing a much lower RDS-on to be 90 milliohms when it's hot. So very important thing to look for because it correlates to obviously device cost and device performance. Please choose the right RDS-on.
That's great information, Guy. Thank you very much. I know you've got some additional information on why this is important. Could you perhaps walk us through that?
Yeah, I've got a couple of slides really, but the first one is a direct comparison of what we've just been talking about. This was a 3 kilowatt, 3.3 kilowatt DC to DC, so typical secondary side sort of DC to DC found in data centers, netcom, that type of application. So 400 volts in, you know, coming from that PFC to, in this case, 48 volts out, something quite familiar with a lot of people. And here, you know, switching, this is resonance, so you're switching at sort of 500 to a megahertz, so it's pretty quick, which is great for silicon carbide. But when you look at the performance of these devices, and we chose two very popular silicon superjunction parts that traditionally are used in these areas, you can see that they're stacking up on the data sheet to be around about 60 milliohm. So, you know, traditionally you would go and seek out a 60 milliohm piece of silicon carbide device. However, when you look at the performance here, you will see that we have deliberately benchmarked here a 120 milliohm silicon carbide Wolfspeed MOSFET. So twice the RDS-on. Normally you would go running away in fear at that. But as you can see here, it compares very nicely to one particular silicon part and compares a lot better to another one. So again, this is a real life example of scoping out the right RDS-on for the silicon carbide. Otherwise, you're going to overrate and overpay.
Yeah, I mean, at the end of the day, cost is king here in a lot of these applications. I mean, although it's not immediately obvious, like you said, on doing that data sheet comparison, it does seem like there are more benefits to silicon carbide than first catches the eye. And certainly if you delve a little bit deeper into the data sheet, this becomes more apparent. Could you perhaps offer a little bit more insight into the cost aspect of this?
Yeah, and this is why I'm centering a lot on choosing the right RDS(on), because obviously with silicon carbide, we preach about increasing switching frequencies, reducing the size and the cost of the inductors and the cooling, all absolutely true and significant cost savings. But a lot of the discussion can boil down to component versus component. And again, choosing that right RDS(on) is key. And I'm only choosing sticker prices here from catalog, the one piece price, which I know is a general term, but it's what people can visibly see. And so if you correlate to the right RDS(on) piece of silicon carbide versus silicon or GaN, so in our case, let's go back to that 60 milliohm data sheet, which is 80 odd milliohms hot. That equals the performance of a 50 milliohm piece of GaN or a 40 milliohm piece of silicon. And when you look at the sticker prices lined up, and I show you some examples here, component to component, actually the silicon carbide MOSFET is the lower, more cost-effective product.
Yeah, it's been great that you could put that into a tabular form for us to understand. That's not immediately obvious, as I mentioned before. Very important nonetheless. So many thanks for the discussion during today's chat, Guy.
Sure, absolutely. Thanks, Simon, for the opportunity.
No problem. So for those on the call, you can learn more about this and other topics by going to our GaN and SiC Tech Hub. You can follow our Ask an Expert link there to ask any questions where you may be facing some similar challenges and need a bit more information. Many thanks for watching us today. Goodbye.
Cheers.
Bye.